This question asks you to analyze 4 statements about how SparseRandomProjection in the SCIKITLEARN library works. I want you to decide which statements are factually correct regarding its parameters and their effects on computation time and accuracy. The dataset you're working with has many samples, millions, many features, thousands, and mostly zeros. This is key because SparseRandomProjection is designed to be efficient with data like this. Your goal is to reduce the number of features from thousands to 500. This is a common task in machine learning to simplify models and improve performance. SparseRandomProjection helps me achieve this by creating a lower dimensional representation of the data. SparseRandomProjection is the specific dimensionality reduction technique used here. It's chosen because it is computationally efficient for sparse datasets. This statement describes a parameter in SparseRandomProjection. Increasing the density, meaning making the projection matrix less sparse, makes the computation faster. However, there's a trade-off. I might lose some information, which is represented by variance, meaning my results will be less accurate. If the density parameter is close to 1, the projection matrix will be almost full of non-zero values. This completely defeats the purpose of using SparseRandomProjection for sparse data, because it loses its computational efficiency. The epsilon, EPS, parameter controls the accuracy. A smaller EPS means better variance preservation, more accurate results, but you'll pay the price in computation time and a denser projection matrix. This is false. While SparseRandomProjection is designed for sparse data, it's not a universally superior method. Other techniques like truncated SVD might be better depending on the specific data and desired accuracy. After using SparseRandomProjection, the result is a dataset with 500 features. This is the lower dimensional representation that I can now use for further analysis or modeling. I see density as the percentage of non-zero values in the random projection matrix. A higher density means more calculations, but it might preserve more variance. Think of it like this. A denser matrix is like using more ingredients in a recipe. It might taste better, preserve more variance, but it also takes longer to cook, more computation time. I understand epsilon as a parameter that controls the level of accuracy. A smaller epsilon means we want higher accuracy, meaning better variance preservation. But this increased accuracy comes at the cost of needing a denser matrix and more computation time. It's a trade-off between precision and speed. Computation time is directly influenced by the density of the projection matrix and the accuracy level, epsilon. A denser matrix with a smaller epsilon will mean more calculations, hence increasing computation time. We need to find the right balance to keep computation time reasonable. Variance preservation refers to how much of the original data's variance is maintained after dimensionality reduction. We aim to preserve as much variance as possible, but increasing accuracy and density might impact this aspect negatively. Finding the perfect balance is key. We need to find a sweet spot. I'm analyzing how the parameters of scikit learn's SparseRandomProjection affect its performance. We'll focus on understanding the density and EPS parameters and how they impact computation time and accuracy. This is key to using this dimensionality reduction technique effectively. The density parameter controls the proportion of non-zero elements in the random projection matrix. Think of it as how full the matrix is. A higher density means more non-zero values, leading to faster computation. However, it also means losing some of the sparsity that makes SparseRandomProjection so efficient for sparse datasets. The epsilon EPS parameter dictates the accuracy of the dimensionality reduction process. A smaller EPS value targets higher accuracy, better variance preservation, but this comes at the cost of increased computation in a denser projection matrix. It's a trade-off between accuracy and efficiency. I'm essentially controlling the acceptable error in the dimensionality reduction. Let's consider how the parameters interact. A smaller EPS necessitates a denser matrix, higher density, to preserve accuracy, thus increasing computation time. This highlights the need to balance computation speed with the desired level of accuracy when you choose the parameters for SparseRandomProjection. It's a classic computational efficiency versus accuracy trade-off. I'll explain this parameter. The density parameter in SparseRandomProjection controls how many non-zero elements are in the random projection matrix. Think of it like this. A higher density means a more populated matrix with fewer zeros, while a lower density means a sparser matrix with more zeros. This directly impacts computation speed and variance preservation. Let's talk about the EPS parameter. It governs the accuracy of the dimensionality reduction. A smaller EPS value aims for higher accuracy, better variance preservation. But this comes at a cost. It usually leads to a denser matrix and thus more computation. It's a trade-off between accuracy and speed. I'll explain this concept. SparseRandomProjection strives for computational efficiency, especially with sparse data. A sparse matrix, one with mostly zeros, allows faster computations because you don't perform many zero-valued operations. The density parameter directly affects this efficiency. A denser matrix loses this advantage. Let me break down this term. Variance preservation refers to how well your dimensionality reduction technique maintains the spread or variability of your data after reducing the number of features. You want to preserve as much of the original variance as possible to avoid losing important information in your data. Both density and EPS affect how well this is done. I'm looking at the parameters for scikit-learn's sparse random projection, a technique for dimensionality reduction. We'll focus on how the density and EPS parameters impact the speed and accuracy of this method. Think of it as fine-tuning a machine. We want it to work fast and accurately. The two main parameters we care about are density and EPS. Density controls how many non-zero elements are in the projection matrix, and EPS controls the level of accuracy we want in our dimension reduction. It's like setting the precision of a measuring tool. Higher precision, smaller EPS means better accuracy but might take longer. Sparse random projection is a specific algorithm in scikit-learn. It's designed to efficiently handle large datasets with many features and mostly zeros by using a sparse projection matrix. A sparse matrix is like a really efficient shopping list with a lot of empty space. It only lists the items you actually need, and that saves space and processing power. I'm evaluating some claims about how density and EPS affect the performance of sparse random projection. We need to determine which statements are factually correct. I'm analyzing how different parameters in scikit-learn's sparse random projection affect its performance. I'll focus on density and epsilon, EPS, which control the speed and accuracy of dimensionality reduction. This question asks you to understand how sparse random projection works and how its parameters influence the outcome, specifically, reducing the dimensions of a dataset with many samples, features, and zeros. We need to analyze the true statements about the parameters to solve this. Scikit-learn is a popular Python library for machine learning. Sparse random projection is a function within it that's designed for efficiently reducing the number of dimensions in sparse datasets with a lot of zero values. This is useful because many datasets, particularly in areas like text processing, are inherently sparse. In considering statement A, increasing the density parameter will speed up calculations because there are fewer zero values. However, this might mean that some important information will be lost in the dimensionality reduction, reducing how well the reduced dataset represents the original one. Statement B is about setting the density parameter close to 1. I'm looking at what happens when the projection matrix is almost full of non-zero values. If that happens, the advantage of using sparse random projection for sparse datasets disappears because it no longer takes advantage of the sparsity in the data, and the computational advantage vanishes. Statement D says that sparse random projection is always the best choice for sparse data. I find that this is false. The best method depends on the specific dataset and what one is hoping to achieve. Other methods might perform better in certain situations.